one.
Okay, thanks for having me here for the last speaker. I have to say I'm probably the last speaker because I do the least accurate open forecast calculations of everyone in this meeting, or I will rather say maybe pragmatic calculations rather than accurate. But I'm sure you can. And also I'm happy to be last because a lot of this work has been done with Mikael. He was the first speaker of this session, so a lot of the implementations in open forecast were done by Mikael. And I would also like to thank Morgan, who is on board now. She has done lots of the calculations. And Johanna, who is the new student, who has done the latest stuff. I would also like to thank Roland for getting the invite into this open forecast community in the first place. And of course also Ignacio for helping me with all things open forecast. And then also now, because you're here, Sergey here, because now we're showing interest in the X-ray spectroscopy of the static and meta complexes. So, and everyone else here, lots of open forecast people with X-rays. So my talk will be about the iron photocatalyst or iron photosensitizer. So what it's doing is it absorbs light and then it will lose an electron that goes into a catalytic reaction. And this is a kind of class of complexes which have been studied experimentally along in Lund in Sweden. And this particular complex is this, it's a carbene complex, two carbene ligands binding into an iron site. And I will tell you first, I will tell you the result of everything first, and then I will give you the details of how we arrive there. First, this complex is in iron 2, it's a single state, and when it gets hit by light, it goes to a metal ligand charge transfer state. And then after this, it branches on this metal ligand charge transfer state. It branches, so 60% goes to a triplet metal ligand charge transfer state, and 40% goes to a metal centered state. And this metal centered state, it vibrates. So it leads to vibrations in this excited state, and that's what you see with the sign structure. And if you look at it, I follow Sonja's kind of excited state dynamic picture here. So we do the excitation. Let's see if I have the light on this page. So excitations, and then with a very short time, it goes to this metal, it goes from the metal ligand charge transfer state into this branching to another metal ligand charge transfer state. But some of it goes to the triplet metal center state. And because this triplet metal center state has much longer bonds, then it starts to vibrate on this side. And the process is fast enough so that the vibration is coherent. So we see this coherent vibrations. This metal center. And so how it's probed. So first we probe it 7 different ways. You excite it with a laser. So and then you follow with an X-ray probe. And then we look at the electronic structure, the X-ray emission spectroscopy, which is the structure, and we look at it with the X-ray diffuse scattering, which is geometric structure. And here lots of photons are going, but basically now you do the valence excitation, and then the valence excitation you follow into the core excitation, so you pick out the 1s electrons. So, and here I use Sergey's code for photoionization. And then it can fall down. Then we look at the initial processes in this states fall down. So the 2p electron is the most likely to fall down. It's a multi-band spectrum, so it can fall down. We get the K alpha X-ray emission frequency. For the 3p with the next highest probability is the 3p, and you get what we call K beta X ds. So with this spectral information, you try to look at, we see in the K alpha XS, which is the 2p to 1 excitation, you see this kind of drop when you do the photo excitation, but then you see oscillation, this coherent, which is this coherent, turns out to be this coherent structure oscillation. But it was kind of unexpected because the K alpha is a 2p to 1s transition, and it should not be very sensitive to the details of the four-way response. So these core transitions turns out to, is it likely that this is a bidirectional spectrum, or is it a coherent transition between electronic states where you think that it would be sensitive? So it was kind of, we see this signal, and it kind of matches with the signal you saw from the X-ray diffuse scattering, which was looking at the structure. So that's the first idea of this coming from a structural oscillation. And the question that we ask calculations to do is to, can we reproduce this sensitivity of that this really should be a structural oscillation? And what we then, this was our calculation. So we need two orbitals. No, we have 2p to 1s excitation, and we need to look at also all the excited states. So this is our kind of standard active space, and we have used here this hex keyword. So this is our final interpretation of the hex keyword in this paper. Basically, it's a core to valence separation. So you don't really need to compute all the states which do not have core points, but there are also high energy states. They are very high energy states. And of course, if you want, you can do double core holes to X. So we tried to do this, but we needed the dynamics into it, and we did not perform any dynamics at the NOSSF level. Instead, we looked at the coordinate, the distortion coordinate from the ground state to the triplet end state, and then we performed the nuclear dynamics on this potential energy surface, and we get kind of a trace. So we get this distance with time. So this should be the average eigenvalue from the time. So, and then it's just, we take every structure along this pathway, and we calculate the X-ray emission spectrum, and then we see how it matches with the experiment. But of course, it didn't work. So when we first started this, we had lots of problems. So basically, the problem is that we have lots of number of states. So we try to do state average calculations with, in this case, 90 states. And especially with some of these doublet states, which you have a triplet in the core, and you have doublet, and then you also have all the doublets, potential singlets with the core hole, etc., etc. So the doublets did not work on this kind. So we had to, and this is the pragmatic part. So we just had to find a way to solve this CI problem. So we did a couple of different CI versions, but basically the CI version that we finally arrived at is that we are renormalizing the CI vectors, and we recompute the sigma vectors every 24 step. It costs a little bit, but it improves convergence. And we limit to 400 vectors. The total number of vectors, we limit it to 400. And we don't calculate any correction vectors for states that are already converged. The first lowest energy states, they are converging fast. And then, so we can use other extra vectors for the states that are different from high energy states. And in the end, it saves us CI iterations, and it saves us computation time. So in the end, then we take all this. I said we take the structures along this trajectory. We calculate the X-ray emission spectrum, and this is the beta emission spectrum. And what we see is a kind of blue shift. So with larger distance, it goes to higher energies, and that means if you are collecting intensity at one energy, or in this case one energy region, this intensity will decrease. So the larger the distance, the lower the intensity. So that's the sensitivity comes from a shift in the spectrum. And now the K beta is a little bit, shape is slightly more sensitive to structure. The K alpha spectra are almost identical, but they just move. And if we take our simulated spectra, so the simulated time evolution in terms of structure, together with the simulated spectra we have for the structure, then it fits nicely with the experimental curve. So we see that it seems that this kind of structural data to the expect, they also give this kind of structural sensitivity that you see in the experiment, and therefore we can more confidently conclude that these are really coherent structural oscillations observed with for X-ray emission spectroscopy. And then we have spent a lot more time recently with the K beta experiment, because the experiment is not so clear. It's not clear if you see oscillations, and we're trying to explain why, and maybe if you can connect at another energy, to which the optimal energy range for connecting these spectra, so you can get better, because in theory, K beta with the form is CP, it's closer to valence, so it should be more sensitive. But on the other hand, the intensity is low. So it turns out that the gain in sensitivity is not more, it's the loss in intensity is dominating. So it turns out the probe that is least close to the valence is the most best one. So if we look at again, what we have was the excitation, and then some part of this went through this coherent structural oscillation, and that's the one we are modeling the X-ray sensitivity to. And our idea about where this sensitivity comes from is because this is the valence excited state. When you kick out the electron, you move on to a 1s or hole electron potential on the surface, or 2p electronic potential surface. And this is so fast you don't move on the potential in this state. You just probe exactly where you were when you did the core excitation. And it turns out that the 2p and the 1s, so we create a hole, it contracts the bonds, actually. So we create a positive charge, it contracts the bonds, but this contraction is different in 2p and 1s for holes, and it's large enough difference so that when you shift the potential energy circuitry, you get an energy shift with the distance. And this is the energy shift that we saw in the initial spectrum. So we can explain the origin of this, and we can explain what makes it more likely to observe this. So in this case, strong bonds, the large energy difference between the potential and the surfaces will make you more sensitive to structural dynamics. And with that, I conclude my presentation. So again, thanks to Mikael and Johanna did the K beta work. Morgan did all the simulation. I think the ones actively fixed the code, so she was happy about that. And then thanks to everyone in the open podcast community and for listening to my talk.